All right, so I'm going to go over question number 9 from assignment 3, dealing with the Coulombs law questions. So number 9 says 3 charges Q1, 2, and 3 are at rest near a negative test charge of Q. And so what we have to assume here is that Q1, 2, and 3 are fixed, okay? And basically we're going to be like, in essence, putting our finger on charge Q, letting it go, and seeing which way it is attracted. Okay, so that's basically what you have to do with these questions. So the first step is to basically list the information, and I like to draw a little diagram to show me just to show what's happening. So step 1, we have Q, which is our test charge of negative, keep that in mind, negative 4.2 times 10 to the negative 6 coulombs. Q1 is positive, I'm just going to write positive so I don't forget, positive 7.3 times 10 to the negative 6 coulombs. Q2, and sorry, this is 0.72 meters north, 34 degrees towards the east. You don't really have to rewrite all of this, but I'm just going to get my information down before I do a sketch. Q2 is negative, and it's 2.1 times 10 to the negative 6 coulombs, 0.59 meters south, 57 degrees towards the east. And Q3 is positive 5.3 times 10 to the minus 6 coulombs, located 0.67 meters north, 72 degrees west. Alright, so just looking that over, looks like that is correct. Alright, so our next step is to draw this. So as we talked about, so Q is the only one that's not fixed, okay, and the rest of them are. So I'm going to approximate where these are. So 0.72 meters away, north, 34 degrees towards the east, this is Q1, and this is positive. The positives and negatives will come into account a little bit later on. Q2 is negative, and that is southeast. So Q2 is down here somewhere, negative. And Q3 is positive, and it is northwest. Positive. So essentially we are asking ourselves, given all of these charges and these distances, if I were to let go of Q, where would it be attracted to? So remembering from Science 9, basically, right? Like charges will repel, and opposite charges will attract. And this comes into play later. So this is basically how we sort of interpret what's going on in the question, and this is all the information the question gave us from the start. Okay, so our second step, I guess, once we've dealt with all this, is to find the forces of attraction / repulsion. And I actually don't care about the sign of these right now. I just want to find the magnitude. So the formula for all of this is F equals Q prime divided by D squared. And the K is a constant, Q and Q prime are the two different charges in question given to us at the beginning, and D is the distance between them in meters. Okay, so the math for this, it's just multiplying and dividing, but the numbers are a little bit awkward to deal with. So I'm going to show you the first couple here, and we'll kind of go through it in real time. So the force between Q and Q1 is Q1 divided by D squared. So what does this look like? Well, it's going to be K, which is 9.0 times 10 to the 9 Newton meters squared per Coulomb squared. That's the constant found on your formula sheet. Multiplied by the charge Q, which is 4.2. I'm not going to worry about the negative sign. 4.2 times 10 to the negative 6 coulombs. And Q1, 7.3 times 10 to the negative 6 coulombs. Divided by the distance between them, Q and Q1 are 0.72 meters apart, squared. Okay, and this is going to give you a number. So I'll do this one with you in real time, and we'll see what we get. So 9.0 times 10 to the 9 times 4.2 times 10 to the negative 6 times 7.3 times 10 to the negative 6 divided by 0.72 squared equals, and this gives me a force of 0.5323 newtons. Obviously we rounded a little bit. Our answer is going to be in 2 sig figs at the end, so the rule is usually 1 more decimal than you need. So I could have done 3. I'm going to keep it to 4 though. So this means that the force between Q and Q1 is 0.5323 newtons. Okay, so what we have to go do now is go through the rest of these charges and figure out the force between them. Okay, so moving this paper up here, now we look at the force between Q and Q2. So this is all in reference to the reference charge Q, which was that negative 4.2. So I'm not going to rewrite everything because K is going to be the same, Q is going to be the same, and then instead of Q1, for this one I'm going to put Q2, which is 2.1 times 10 to the negative 6 coulombs, and the distance between Q and Q2 is 0.59 meters squared. Alright, so keeping that the same, we have 9.0 times 10 to the 9 times 4.2 times 10 to the negative 6 minus 6 times 2.1 times 10 to the minus 6 divided by 0.59 squared equals, and this gives me 0.2280 newtons. Alright, so I'll tell you right now, on the exam there is a question with 4 or 5 charges, and so you have to do this. In this case we only have to do 3 because there's a reference charge plus 3 charges. But if there was 10 charges plus a reference charge, you'd have to do this 10 times. So KQ is not going to change. My Q3 is 5.3 times 10 to the minus 6 coulombs, and the distance between those ones is 0.67 meters squared. So my last force here is 9.0 times 10 to the 9. Feel free to save that value in your calculator if you want to do that. Times 4.2 again, times 10 to the negative 6, times Q3, which is 5.3 times 10 to the negative 6, divided by 0.67 squared equals, I get 0.4463 newtons. Alright, so I found my 3 forces, basically. So Q is going to feel 0.53 newtons towards Q1, 0.2280 newtons towards Q2, and 0.4463 newtons towards Q3. Now, what direction are these going to go? Well, if we look back at our original drawing, which hopefully you have handy, don't have to keep switching screens, we have to look, are these charges going to repel or attract? That is based solely upon their charge. So if we look at Q and Q1, they're going to attract because they are opposite charges. So Q is going to be pulled in the direction of Q1. So we can actually solve this right now. So step three is to find basically the components of the forces. Okay, so Q and Q1 we said is going to attract. So I'm going to actually redraw just this. This is Q. Q1 was over here, and I'm going to write now the force vector. So the force felt between Q and Q1 is 0.5323 newtons, and the direction here, this angle, given to us is north 34 degrees towards the east. Let's write that's 34 degrees. So we have to then find the components. So I'm going to call this component the force horizontal from Q1 and the force vertical from Q1. So now this becomes a review of vectors at this point. So if I try and solve for FH1, how do I find that? Well, I go opposite, so I have to use sine, sorry. So sine of 34 degrees is FH1 over 0.5323 newtons. So the horizontal force is going to be sine 34 times 0.5323. So this is 0.2977 newtons. And the vertical is going to be cos of 34 times by 0.5323. So this should look familiar from when we did vectors way back. And this gives me 0.4413. And 4 decimal places is more than enough. Now, we have to look here. They are both positive, right? This is towards the east. We now have this Cartesian plane here. This is east, this is north. These are both positive values. So we have the vertical and horizontal forces felt between Q and Q1. And so we have to do this for the other forces. So if I go back and I look now, between Q and Q2, they are actually both negative. Okay, so we have to take this into account. So now I look at between Q and Q2. Now, Q2 was down here, and Q is in the middle. Because they are negative, it's actually going to push into the opposite quadrant. So Q2 was south 57 degrees east, which means because they are like charges, Q is not going to be attracted to Q2, it's going to be pushed into the opposite quadrant. So I'm actually going to draw this diagram this way. And so this is 57 degrees here. But we still have our right triangle. Okay, and the force felt was the one we calculated to be 0.2280 newtons. So now I have the force from 2 horizontal and the force from 2 vertical. All right, so we can find this using sine and cos. So the horizontal is 0.2280 times sine 57, and the vertical is 0.2280 times cos of 57. So we'll just do the math here. Try not to make any mistakes. Is 0.19 newtons, and 57 cos times 0.2280 is 0.1242 newtons. Now, the vertical is positive because we're going north, but the horizontal is negative because we are going towards the west. Okay, and that's going to be important when we find our resultant shortly. All right, last one. So the force between Q and Q3. If I look back at my original diagram, Q3 is positive, Q is negative, so it's going to be attracted to Q3, so we don't have to do anything fancy there. So it is going to pull it into this quadrant as well, and it is north 72 degrees towards the west. The magnitude of the force was 0.4463 newtons. So we have the force from 3 horizontal, force from 3 vertical. And we're going to solve that. So F3 horizontal is 0.4463 times sine of 72, and the force 3 vertical is 0.4463 times cosine of 72. Again, the horizontal one will be negative and the vertical one will be positive, just based on the direction. 72 sine times 0.4463 gives me 0.4245, and 72 cos times 0.4463 gives me positive 0.1379. And these are all newtons. Okay, so you see we have 3 fixed forces, 1 test charge, so that led to a total of 3 force calculations, and all of which had to be broken down into vectors. Alright, so our last step here is to find the resultant. Alright, step 4 is find the resultant. So I need to find the resultant vertical and the resultant horizontal. So going through, checking the signs again, my vertical from the first one is positive, so 0.4413. My vertical from the second one is also positive, plus 0.1242. And the third one is positive, so this charge is definitely going to be moving up. And these are all newtons. Okay, we'll combine those. And the horizontal, in the first one the horizontal was positive, and that was 0.2977. In the second one the horizontal was negative, so minus 0.1912. And in the third case it was also negative 0.4245. So just based on those diagrams, the initial thing we drew, it's likely that this charge is going to go this way somehow, right? Just based on, it's not going to go down. And I'm going to predict to the left. So let's combine this, see what we get. So 0.4413 plus 0.1242 plus 0.1379. It's 0.7034 positive. And the second component here, subtract because of the negative sign. Subtract 0.4245. Gives me a negative horizontal of 0.318. Alright, so now we draw our resultant. And this is again review from vectors. So we have a positive vertical and a negative horizontal. So it's going to be in this quadrant somewhere. Okay, my vertical is 0.7034. My horizontal is negative to the west, 0.3180. So we have to find the magnitude and this direction. So using Pythagorean, r squared is basically the horizontal squared plus the vertical squared. I'll let you type in the numbers here. So 0.3180 squared plus 0.7034 squared equals, square root that gives me 0.7719 newtons. So that's my resultant force. And then the angle, we can use tan inverse opposite over adjacent. So these numbers, 0.3180 divided by 0.7034. Second feature, tan, gives me an angle of 24.33 degrees. So if we were to put these to 2 sig figs, sorry I got a little cut off there, just the math we just did. What does this mean? Well, this means that our test charge feels a force of 0.77 newtons north, 24 degrees towards the west. So if we were to let go of our finger in that initial diagram, this charge would feel that force and would move this way. And there's our final answer. So hopefully that makes a little bit of sense. Just to quickly review, excuse my papers here as I try and make this video quickly. So first we had our information, which I like to write down, doing a little picture of what's happening, and then calculating the forces. You'll have to do this equation the same number of times as you have other charges. So we had one test charge and then 3 fixed charges, so I have to compare each of these to the test charge, meaning 3 equations. So we found the forces, just the magnitude between Q and Q1, Q and Q2, Q and Q3. Then we go back and we look at the components of the forces. Now this is based on the charge, whether it's positive or negative. If they are opposite charges, they will attract, and you can just use the initial direction given to you. If they are negative charges, like I believe Q2 was, you have to assume it's going to be repelled into the opposite quadrant and adjust your vectors accordingly. Once you have all the components, in this case we had 6 components, 3 vertical, 3 horizontal, you then construct your resultant, and you could have up to 10 different things here. I would expect to do one between 4 and 5 on the exam. So here's our vertical components, being careful of the sign, which we determined in the last step. Once you know the vertical was positive, we drew it up. The horizontal was negative, we drew it left. And then you simply use your knowledge from vectors using Pythagorean and tan to figure out the resultant vector magnitude, 0.77 newtons, and the resultant angle using tan. And that is how you do one of those questions. There is a couple different variations, but that is what you can expect on the exam and on the final. So let me know if there's any questions. Hopefully that makes sense, and good luck.